Hello, this is a video on Euler's method. I watched the movie Hidden Figures tonight with some students. They were watching it and I went and joined them. And I'm at Houghton College. And by the way, I'm not a mathematician, so Houghton College is not responsible for my shoddy math. I actually think this will be an accurate video. I like the movie Hidden Figures very much. I actually had these PowerPoints mostly ready to go about 8 months ago. My daughter was in high school then in March and was taking second semester calculus at Marion High School. And now she's gone on to glory in Pepperdine. But so I had this PowerPoint all ready to go. And since I watched the movie tonight, I thought, well, I might as well go ahead and finish that video. By the way, in the movie, Jim Parsons says, "Why, that's ancient." It's not ancient, Jim Parsons, silly Jim Parsons. It goes back to Euler in the 1700s. And in fact, my daughter was studying it in high school. It's in James Stewart's Calculus 6e, which I'm following along with here. And so it seems to be a fairly well-known method, not some obscure kind of thing. Of course, I don't know how they taught calculus in the 1950s, but Euler's method. Um, uh, it's a way of approximating messy differential equations. So let's dig right in. So let's take this messy differential equation, y prime equals x plus y, where y prime is, of course, the derivative of y. What makes it messy, of course, is that we have both y and its derivative in the same equation. There is no kind of formula answer to this. In other words, you can't come up with, well, obviously the solution, y equals blah. You can't come up with a formulaic solution. So you have to use a numerical approach, which is, of course, what the movie basically is saying, that because they couldn't come up with a formula for the go no go point to return to Earth, to switch from an elliptical to a parabolic orbit, that they would need to do an approximation for it. And of course, they bring on the IBM computers to make it a very great approximation, or really good and quickly derived approximation. Well, so basically, let's say 0, 1 is a point that's a solution to this. So at 0, 1, 0 plus 1 is 1. So the slope at that point is going to be 1. Now, by the way, you can see that's not the slope of this line. It's poorly drawn, bad Ken, so sorry. This line with a slope of 1, allegedly, is a good approximation at 0, 1, but you can see it's a really bad approximation when we're out here. So what Euler suggested is, what if we go in increments? We go little increment, we stop, we look around, we reassess the equation, and we keep moving. So let's say we decide, and this is just arbitrary, we decide to use increments of 0.5 for this. So what is the y? So 0.5, we know what the x coordinate is here. What would be the y component here? Well, this had a slope of 1, right? So 1 equals 0.5 plus 0.5. And so it's going to have gone up 0.5 from where it started. So the point here would be, and again, poorly drawn, would be 0.5, 1.5. So there we have a point. It's a little bit off, but it's in the ballpark-ish. And of course, what we then do is we draw a new line from there. And so the slope of the new line is going to be 0.5 plus 1.5, or 2. So now we've got another line here. Again, the further you go out, the further it's going to be from the function itself. But we can come up with a formula for this new line, because y2 minus y1 equals the slope times x2 minus x1, right? This is the point slope form of a linear equation, right? So y2 minus y1, there's y1, equals the slope, which is 2. Remember, you add these together and you get a slope of 2, times x2 minus x1, and there's x1. So now we have another line slope that gets us a little bit further. And so what you do is, the smaller the step size, as you make these incremental moves, the smaller the step size, the more accurate your numerical approximation is going to be to the function you're trying to approximate. And in general, we can say, so if we call the increment h, again, this is x sub aught, y sub aught, or x0, y0, and then another point after going the increment, x1, y1. So if we take this basic framework, we can basically say that the slope, if the slope is f of, the initial slope is f of x sub aught, y sub aught, aught is 0, so x0, y0. If that's the slope, it's going to equal the rise over the run, which is delta y over delta x, right? And we're defining delta x as the increment, right? So then if we multiply, by h, we've got h slope at this initial point equals y2 minus y0, or y sub aught. So if we solve for y1, that is the new y, it's going to be y1 equals y sub aught plus the increment times the slope, okay? Now, what we then do is for each subsequent increment, we basically plug in the next number. So if we go to y2 is going to equal y1 plus h times the slope at x1, y1. And then that'll give us y2. Then we plug it in to get y3. y3 equals y2 plus h f x2, y2, and so forth. We keep doing that to get subsequent increments along the line. So here's an example for increments. So let's say that we're doing 0.1, increments of 0.1 for this same function, by the way. So 0.1, 0.2, 0.3, 0.4, the increment is h equals 0.1, right? We're increasing it by step by step. So here we have approximate values for what y is at each point, or what the solution is for the y value at each point. And there you go. This is only as accurate as 0.1, right? The smaller the step size, the more accurate it's going to be. So for example, if we're trying to figure out what y is at x equals 0.5, the smaller the increment, the more accurate it gets. It approaches a limit, and the limit is the true solution to the differential equation, what y actually is at that particular point. So it looks like the 7 is secure, and I'm guessing the 9 is probably secure. So the further down the smaller the increment, the more accurate it gets. At 1, again, I think the 4 is secure, maybe the 3 is secure, but the smaller and of course computers can approximate this by just making it a really small step size, and you basically get a close approximation for what the actual solution is to the differential equation using this numerical crunching because there's no formula that you can use. Well, this has been a video on Euler's method.